Hi everyone, and welcome to another edition of Existential Physics with Ogar Plinkleton. I'm Ogar Plinkleton. In today's video, we're going to be exploring the magic of light passing through a single slit. We'll be looking at the diffraction and the interference patterns that are caused by the light diffracting as it goes through the slit. But before we get started, I need to put some notes up on the board. This won't take very long. Okay, in order for us to create interference patterns that we can see when light is diffracted through a single slit, our light sources need to be coherent. And what that means is the light sources have to have the same frequency, have a fixed phase relationship, and pass through the same region in space. Okay, what I've drawn here, this is our slit. This is actually a 35 millimeter slide that has a slit into it. You're looking down on the slide. Here's our laser. We're going to be using a green laser, and the light is being shined onto the slit. Because a laser provides coherent light, that's going to be our light sources. And when it goes through the slit, it acts as an infinite number of light sources. And so the light is coming through and it's diffracted. Which means it actually spreads itself around the edges of the slit. And just trying to make some pseudo waveforms here. And there's an infinite number of these waveforms. Okay, and as they go through, they're going to add up. And by add up, I mean by superposition. As I just said, the light adds by superposition. So if we have two waves that are in phase, like these are, this is just the wavelength lambda, so they're the same frequency, they're in phase and in the same region of space, this wave plus this wave is going to equal that wave, with twice the amplitude than these two. They simply add up. And the way that manifests itself in light, you're going to get a very bright light where this occurs, where it's known as a maxima. This is known as total constructive interference. So if we have total constructive interference, we can also have total destructive interference. Okay, here you can see that the waves are shifted by lambda over 2. And they line up this way. And so they cancel one another. This wave plus this wave gives you the null set. And that is going to be a place of complete darkness, otherwise known as a minima, and that's total destructive interference. Now, these are the two extremes, total constructive, total destructive, and then anywhere in between. where they add up, but they're not completely constructive or completely destructive. So there's light, but it's not as bright as this, nor is it total darkness. Here's our setup, and there's the 35 millimeter slide I was telling you about. We're going to be using the first slit on that slide that's marked with a red arrow. That's 0.075 millimeters wide. I'll put in the laser and turn it on, and I'll move the slide out of the way, and you'll see it's just a blob of green light on the screen. And I'll turn the lights off, and you can see it's just a blob of green light. Now I'll move the slide in front and shine the laser through that first slit. And it's no longer a blob of light. Let me turn the lights off, and I'll also zoom in on it. And now you can see the areas of brightness and the areas of darkness. The areas of brightness are the maxima caused by total constructive interference, and the areas of darkness are the minima caused by complete destructive interference. The bright spot right in the middle is known as the primary maxima, and the bright spots to the left and right of that are known as the secondary maxima. And of course, the places where no light exists are the minima. All right, that's it for this video, and I hope you enjoyed it. Next video, I think I will do something with light as well. And I just wanted to share that I've just published my latest book that haven't been in print for close to 25 years. And this is available on Amazon. And if you'd like to support me in any way, it's not that expensive. It's not a very thick book, but I think it's quite good. Anyway, until next time, this is Ogar Plinkleton. Be safe.